So in the last episode, we looked at an easy Java interview problem called unique characters in a string. Just as a reminder, we receive a string and we need to return true if all the characters in the string are unique. So for example, if we receive ABCDE, we return true. And if we receive MADAM, we would return false because all the characters aren't unique. So in that episode, we presented two different algorithms to solve this problem. One was a linear time algorithm, and one was on the order of n squared. So after studying the algorithms for a while, I wondered, are there actually any real-world differences between the two algorithms in terms of speed? And also, is the linear time algorithm always better than the n squared algorithm? So I decided to run a little experiment in which we'll test the real-world performance of both algorithms. So as a quick reminder, this is our n squared algorithm at the top here, and it works by looking at the first character and then scanning the rest of the string looking for that character. If we find a repeated character, we return false immediately. Otherwise, we move on to the next character and again scan the remainder of the string looking for that character. So this is our n squared algorithm up here. Our linear time algorithm used a hash set to keep track of all the characters that it's seen before. So as we go through our string, we add characters to this hash set one at a time, and as we encounter a new character, we check the hash set to see if it's been seen before. If it has, we can return false. If it hasn't, we just add the character to the hash set and move on to the next character. So one thing I noticed was all the operations on the n squared algorithm were very simple. We're just doing simple arithmetic operations, getting the length of a string, getting certain characters at certain indexes of the string, all very simple. Whereas with our linear time algorithm, we instantiate a hash set, we check if a character is in that hash set, and if it's not, we add it to the hash set. Now these are still constant time operations, but they're more expensive constant time operations than the simple operations in the algorithm at the top. So I wondered what the real-world performance differences between these two algorithms would be. Will the linear time algorithm down here using the hash set always be faster? Or will the simple operations used in the order n squared algorithm at the top beat out the hash set operations in terms of speed? So for our experiment, I started with string length 10, and then incremented to a string of length 20, then 30, then 40, and so on, all the way down to strings of length 90 as the input string. After strings of length 90, we start to run into the problem of not having easily typable nor printable ASCII characters. So I decided to stop at strings of length 90. Also, because we want to test worst case performance of both algorithms, all the characters in all of these strings are unique. So for every input, we're going to be running through both sets of loops here and returning true at the end. Similarly, down here, we're going to be adding all characters to the hash set and then returning true at the end. So it's a true measure of worst case performance of both algorithms. And to help reduce variability in the results, because calling these algorithms simply once for each input would be too quick and we get kind of variable results, I decided to run through each algorithm 1,000,000 times for each input. So for input string of length 10, we run this algorithm 1,000,000 times, count how long that takes. Similarly down here, for a string of length 10, we run this algorithm 1,000,000 times, see how long that takes, and then go up to the next string of length 20 and repeat that. So each algorithm is run 1,000,000 times for each input string. So for our results, we've got the input string size here from 10 all the way up to 90, and our results are in number of milliseconds required to execute the algorithm 1,000,000 times. So you can see the blue line here is our n squared algorithm. The red line is our linear time algorithm that uses the hash set. And you can see the hash set algorithm is actually slower to start with for smaller inputs. It only starts getting faster right about here at around n equals 30. And that's because of those hash set operations, contains and add. While still constant time, they're more expensive than the simple operations in the n squared algorithm. Eventually, though, as n goes larger, the sheer number of operations required in the n squared algorithm takes over and becomes more expensive than the hash set operations in the linear time algorithm. Certainly, asymptotic complexity matters. It's important to understand how your algorithm performs as the size of the input gets large. And you can see the very clear differences between the linear time and n squared algorithms on the graph. In our example, we only looked at inputs of size 90. You can imagine what would happen if the string input was of length 1,000 or 1,000,000. The difference in the running time of those algorithms would be just astronomical. Another thing is that the hash set methods can be relatively expensive. They are constant time, but there is a cost to using them. And you need to be aware of when you use those methods, because sometimes more simple operations can be faster. It's also important to remember that a slower algorithm can actually be faster for real-world inputs. So imagine we actually had to use one of these algorithms to decide whether all the characters in a string were unique or not. And we knew that the input string would just be words in English language. Well, in that case, virtually all input strings are going to be of size less than 30. There aren't too many words in English that are greater than 30 characters. So if we want to have the absolute best performance for our algorithm, it would be advantageous to use the slower n squared algorithm over the linear time algorithm that uses hash sets. Anyway, hope you found this enjoyable, and we'll see you next time.